Hello everyone, let's study about potential energy of a dipole in an external electric field. To understand this, let's take a case where we have an uniform electric field and let the field strength be E. Suppose assume that a dipole is oriented along the field in such a way that the dipole has two charges. Let this charge be minus q and this is plus q. Charge here is minus q, this is plus q. So dipole moment would be from minus to plus like this. What dipole moment is? Let the angle made be some theta. Now suppose imagine that we are rotating the dipole. So in this case we saw that a torque will act on a dipole and the torque is given as P into E into sine theta. Now the torque would act in clockwise direction, so the clock would tend to rotate it and this clock would tend to align the dipole along the electric field. Suppose if we apply an external torque, like this, we call as tau external. Now this torque is applied to counter this torque, and because of the applied torque, imagine that the dipole is aligned something like this. It's aligned like this. So it's gone from this to this orientation. Charge is kept here. This is like minus q. This is like plus q. So that the charge here is minus q. Charge here is plus q. And we are rotated by a very small angle called as d theta. Keep in mind that d theta is a very small angle. So for the small rotation, we do some work because we are doing work against the system's torque. The system itself would tend to align the dipole along the electric field. So here we are doing external work. We are applying external torque to rotate it. We are doing work here. In that case, the work done by us we call as dW. That work done is equal to tau external into d theta. Now here, this dW is equal to the external torque is just to balance this torque. It's equal to P into E into sine theta into d theta. Let's assume that we move this dipole from an orientation like this. This is what is the electric field. We move it from one orientation to other orientation. That is, dipole is aligned like this initially. We moved from this orientation to something like this, so that the angle initially what the dipole makes, that is this angle here, is say theta 1, and we moved from theta 1 to theta 2. We are moving from the position 1 to position 2. We are moving it like this. For this, the total work done. So we already saw that the work done is equal to P into E into sine d theta. So the work done to rotate it from orientation 1 to 2, that is equal to integrating dW, that will be integrating PE sine theta into d theta from theta 1 to theta 2. Since the field is assumed to be constant, and also since P is constant, P and E comes out. So what remains here would be integral of sine theta d theta. Integral of sine theta d theta, that is equal to P into E into minus cos theta, theta 1 to theta 2. Put the values here, P into E into A minus outside, it becomes cos theta 2 minus cos theta 1. So this is the work done, and the work done is stored as potential energy. So work done to move from 1 to 2 would be equal to potential energy. But recall that work done to move from initial point to final point is equal to UF minus U initial. So we can write this also as U2 minus U1, that is equal to minus of PE into cos theta 2 minus cos theta 1. What the expression is for two rotations? We'll open the bracket here. So U2 minus U1 is equal to minus P2 cos theta 2 minus of minus PE cos theta 1. Observe carefully here. Look at the form here. There's U2, there's something here, minus sign, a minus sign here, and there is U1 here. So this would mean that the potential energy comparing these two terms, that is comparing left hand side, right hand side, we can say that the energy would be of the form minus P into E into cos theta. That is comparing this term here with this term and comparing this term with this term, we get that U is equal to minus P into E into cos theta, or U is equal to minus of P dot E. We can get this in many other forms also. That is, from here itself we can get this equation. So here we need to find reference point. Keep in mind that in case of potential energy, we always talk about difference in potential energy, because energy on its own is meaningless. Always it is the difference in potential energy. For that we need a reference point. So it would be common sense that we can set the reference point to have energy to be 0. It's like this. For example, think that we have a pencil of length 5 cm. Suppose you want to measure this pencil using a scale. That is, we have scale like this. Now imagine that I place a pencil from this point to somewhere else. Its length is 5 cm. So it will go from here to here. This is what length would be. Instead of this, if I place a pencil, suppose somewhere from here, it will go till this distance. So in this case, the length would be difference of these two values, which is same as 5 cm. Same here also. But instead of doing this, we can make it more simple also. So here the reference point is 2. The reference point is 2 in this case. It is 4 in this case. You can make it more easier by choosing the reference point to be at the origin itself. So if we take this as a reference point, then the length of scale would be just 5 cm. It will be from here to here. Keep in mind that wherever the reference point is, the length is same only. It's not changing. But the calculation becomes simpler if the reference point would be having a 0 value. In terms of potential energy, we can say that we can take a reference point such that at that reference point, potential energy is equal to 0. Recall in case of 2 point charges, that reference point was taken as infinity because U for 2 charges was given as K, Q1, Q2 by R. So if R tends to infinity, then U will become 0. So for a system of 2 charges, the reference point would be infinity. But here we can't move the charge to infinity. We can't move the dipole to infinity. So what you can do here rather than that is, if you look at this form, the form here is U is equal to minus P into E into cos theta. If we put theta as 90 degrees, then U becomes 0. So the reference point for a dipole would be an alignment such that the dipole is perpendicular to the electric field. So, in case of a dipole in an electric field, the reference point is such that the dipole is normal to the electric field. It's placed like this. This would be the reference point. This would be 90 degrees. So in that way, what we get is, in this case, energy becomes 0. So energy is negative here. U is equal to minus of P into E into cos theta. That is because if we keep it somewhere, if we keep it an angle like this, see the angle here is 30 degrees, then the system itself will do work. That is, we keep it here, the system itself will try to rotate it. We have seen in the previous discussion that whenever energy is negative, it means the system itself does work. Here also the system itself would rotate it. That's the reason that U is equal to negative. And second point here is, we want to find what is the difference between two orientations. That is, we moved from an angle of 30 degrees to an angle of say 120 degrees. So theta 1 is 30, theta 2 is 120 degrees. In that case, the work done to move from 1 to 2 is U2 minus U1 is equal to minus P is common. It becomes cos theta 2 minus of cos theta 1. Okay, this is what is the work done. It's the same as what we got earlier also. This is what we got earlier here. So this is the potential energy of a dipole in an external field.